Hello guys, welcome. So first of all, a small caveat: if you don't know any of the tools or theory I'm going to be using today, well check out my YouTube channel, because there I give full lectures on every single tool or theory that I use. And right now, ladies and gentlemen, x, y, and z are positive real numbers such that the sum of their squares is equal to a3. We're supposed to prove that x squared plus y times z all over x squared plus y times z plus a1 and a cyclic sum taken all over it is less than or equal to a2. Perfect. So how do we get about this problem? Well, first of all, I would love to simplify this stuff, well, as much as I can, because this is honestly a mess, an improper mess, I would even say. And so, well, first of all, you see, those expressions are the same. I mean, the expression in the numerator and the one that we are adding 1 to in the denominator, well, those are the same expressions. And this is actually the case for every single term in the sum that we are supposed to estimate the upper bound on. And so, well, I would like to actually make a nice substitution right there to, well, simplify stuff a bit. So I would like to take some kind of an a and set it equal to x squared plus y times z. I would like to take some kind of a b and set it equal to y squared plus x times z. And I would like to take some kind of a c and set it equal to z squared plus x times a y. And why did I do this? Well, now what I can do with this substitution is rewrite the entire problem statement as a all over a plus 1. Yeah, maybe this was a little bit too long of a fraction line. Yeah, plus b all over b plus 1 and plus a c all over c plus 1 is less than or equal to a2. Perfect. Okay, lovely. Obviously, our condition right now kind of changes dramatically, because, well, x squared plus y squared plus z squared was equal to 3, and we see that, well, a plus b plus c is equal to, well, x squared plus y squared plus z squared plus xy plus zy plus xz, which is, well, as x, y, zy and xz are all positive real numbers and non-zero, is strictly greater than 3, and so what we're getting is, well, a plus b plus ac is strictly greater than 3. That's actually a rhyme, it's a nice one. Okay, perfect. So, well, right now you see, guys, we have 3 expressions. Each and every one of those is in terms of a single variable, and we're supposed to estimate a numerical upper bound on that. Sounds like a Jensen inequality, doesn't it? So I would like now to create myself a function. Let's call it f of x, let's say. And I would like to set it equal to x over x plus 1, such that, well, this term right here is going to be f of a, this is going to be f of b, and this thing right here is going to be f of, oh, not f of b, it's going to be f of c. Perfect. And why did I do this step right here? Well, I did that because there is this nice stuff called Jensen's inequality. If you don't know what I'm talking about, well, then check out my YouTube channel, because there I have a lecture on that, by the way. Yeah, so this states that for the case of 3 variables, we have some 3 variables, a, b, and c, let's say, then, well, the average of the function values for those 3 variables is going to be less than or equal to the function value for the average of those 3 arguments, those 3 variables. That's so-called Jensen's inequality, but it holds only if f is a concave function. Okay, perfect. If you don't know what, well, a concave function is, well, also check out my video on Jensen's inequality, because there I give an explanation on that. Okay, perfect. Well, so now if we manage to prove that f of x is equal to, is concave, not equal, if we manage to prove that it's concave, well, then this inequality right here is going to change into something like this. This is going to be actually less than or equal to 3 times, well, a plus b plus c all over 3 all over a plus b plus c all over 3 and plus so on. That's definitely one too long fraction line right there. Okay, perfect. Oh, I accidentally erased the 3 right there. Okay, perfect. So, is f of x concave? Well, there's no better method than, well, checking what its second derivative is. If the second derivative is negative, then it means that the slope of the tangent line to the curve itself decreases. as we move along the positive x direction, and so well then the function has to look something like this, and well this is a concave function indeed, and so we are looking for a negative second derivative in this case. So well, calculating it, let's first of all try and see what the first derivative is gonna look like. So quotient rule, we get that 1 is going to be equal to the derivative of x, which is 1 times x plus 1, so just an x plus 1, and then minus the derivative of x plus 1, which is 1 times x, so minus x, all over the square of the denominator, which is x plus 1 squared. And now let's, this is actually equal to, by the way, 1 over x plus 1 squared, and so now second derivative is going to be the derivative of the first derivative perfectly. So this is going to be actually equal to, well, with the chain rule, let's set u to be equal to x plus 1. We are getting negative 2 all over the x plus 1 cubed multiplied by the derivative of x plus 1, but it's 1, so I'm not even writing it down. And so what we're getting is, well, this is actually always less than or equal to 0, and well, that has to be always less than or equal to 0, because the numbers we're dealing with are only positive real numbers. Those are only the numbers we care about in this problem. Perfectly. Okay, so we get that f is a concave function. F is concave. Or maybe, let's get fancy here. Perfect. Okay, so well, we get that this inequality right there is true. The problem is that it does not solve a problem. You see, a plus b plus c is greater than 3, and so this thing right here is actually, after maybe some space here, is gonna actually be not good there, but well, who cares? Let's proceed further. So this right there is gonna be actually greater than 3 times, well, 3 over 3 is just 1 over 3 over 3, which is 1 plus 1, so 2. It's going to be greater than or equal to 3 over 2. We have absolutely no idea if this is going to be less than or equal to, and if this is going to be less than or equal to 2, well, no idea. So we have to prove right now that this thing is going to be less than or equal to a 2. Okay, so, well, using a, b, and c, we're not getting there. We have to switch once again to x, y, and z, and use, well, those numbers to prove our inequality. So what we really want to prove right now is that 3 times, well, a plus b plus c, which is equal to x squared plus y squared plus z squared plus xy plus zy plus xz. So actually 3 plus xy plus zy plus z plus xz. So I'm just gonna write 3 plus xy plus xz plus zy, I guess. Yeah, all over 3. All over once again. A big 3 right there. 3 plus xy plus xz plus yz all over 3 plus 1 is gonna be less than or equal to 2. And you know what? For simplification's sake, I'm just gonna say that this stuff, or maybe not this stuff, I'm gonna say that xy plus xz plus zy is gonna be some kind of an n. Yeah, what do you think about that? Yeah, n. Perfect. I know that my n was kind of funny, but whatever. So we would like to prove that 3 multiplied by 3 plus n all over 3 all over 3 plus n all over 3 plus 1 is less than or equal to 2, which means that, well, those two are going to cancel each other out. 3 plus n is less than or equal to 6 plus 2 times n all over 3 plus a2, and so, ladies and gentlemen, actually that n is less than or equal to 3, and so xy plus zy plus xz is less than or equal to 3. But what is 3? Well, 3 is xy plus yz plus x squared plus y squared plus z squared. And so what we really want to prove is that xy plus zy plus zx is less than or equal to x squared plus y squared plus z squared. And well, this is gonna solve our problem for good. So, you know, let's do it. I'm gonna just bring a little bit more space here. I'm not doing that. So We want to prove that, maybe I will write it down once again, whatever. So we would like to prove that x times y plus z times x plus z times y is less than or equal to x squared plus y squared plus z squared. And so what? Yes, you know what? We have three ways to deal with that. We have rearrangement with mere heads, and we also have, I think my favorite one, so A and G inequalities. So, well, first of all, a nice thing is that, well, x plus y all over, x squared plus y squared all over 2 is greater than or equal to the square root of x squared times y squared, so just x times y. Then, second part, we have that x squared plus z squared all over 2 is greater than or equal to x times z. And the third part, we get that z squared plus y squared all over 2 is greater than or equal to zy. And right now, we're just adding all of that stuff and I don't know, making a nicely looking plus with a fancy rich color. We're getting x squared plus y squared plus z squared greater than or equal to x times y plus z times y plus z times x, which, ladies and gentlemen, solves a problem, proves the inequality, estimates the upper bound, everything. So thank you guys for watching, and well, hope to see you in the next one.